Hello, good morning, everybody.
Good morning.
Yeah, hope others will join us in the meantime. We shall go through what we were doing the last session.
Yes, sir. Good
There is
morning.
little disturbance in the background. There's some construction work going on. So, if you recall, in the last class, we discussed how to create a daemon. So, daemon creation process involves several steps that you have to fork twice and then create a session, change the directory to root, unmask, and close all the file descriptors, and anything that you want to uh, print from the daemon, it should be in the log file, syslog, using the syslog function. This is what we saw in our previous session. Now, what is the utility part of it? How can I utilize a daemon to do certain tasks? In our previous session, we only saw how to demonize a process. But let us see how we can keep this demonization process as a function and the daemon does some meaningful thing. So for that, I have one program here, demonize.c. Now just observe this program that I have kept what we did in our last session as a function here, void demonize. So I am doing exactly the same thing we did last time. That first thing I fork, check whether the fork went successfully and make the parent exit. Okay, so that it is not the process group leader. Then I create a session, set SID. Again, we have to block certain signals which was not done last time, but this is one additional step you have to do. And then again fork, because this time you want the child should not be a session group leader. So you do a fork again and make the parent exit. Then you unmask the file protection masks, change the directory to root so that any files which are open in other directories are accessible. Then close all the file descriptors and open all this. So this is the demonization process. Now, how can I make a daemon perform some meaningful thing? So first step in the program of a daemon is demonize. That is, convert the process into a daemon. Now, what this daemon does, it will open a file. In fact, I'll be dealing with file opening and file creation in great detail when you go to the file system. But let us understand that there is a system call called as open, where you specify the path where you want to create a file. So I am going to create system.log in the working directory of mine, that is home/sfr and lecture 6. This is the file name. Now, in what mode you want to open the file? I want to open this file only write mode. Then if file does not exist, it will create that, and whatever you write will be appended. So these are the flags that you need to specify as part of the file opening process, and give the file different permissions. That is, the owner will have read write permission, others will have only read permissions. And this open will return an integer value called as file descriptor. So what is this file descriptor? What it actually means we shall see in great detail when we look at the file system as a separate topic. Now within this daemon, what I want to do is I want to continuously put some message into the file. For that, we need to declare a buffer. I need to create that string constant. So the string is message from the process, that is I am going to do get PID here, and I want to print the time when this message was last printed. So there is a time function using which you can get the current time, and since it is in certain format, it should be converted into string. So the cTime function will do that, and you have to call the function time to get the current time and make it part of this buffer. Once you have it, you use the file descriptor of the file that you opened here to write into that file. So the way to write is simply write fd the buffer which contains the message and the length of the buffer, and sleep for some time and keep doing this indefinitely. So this is a daemon which is continuously putting out messages into the log file. So let's see how it functions. So first thing is I need to compile this -o /Daemonize. Now as you can see, it will immediately come back. Then we need to check whether it is working or not using xj. As you can see, there is a process Daemonize running in the background with PID 2679. Now has it created a file? We have to do an ls and see. As you can see, there is a file system.log. So if I check the content of this, you will see it has written the messages at that particular time. And if you see the PID, which is the third column here, 2679, exactly corresponds to the PID that it displayed when I gave ps-xg. So 2679. So the process is correctly writing into the file continuously. Okay. So this is one utility of a daemon which continuously does something. Okay. Alright. Now the next thing to learn in Unix is what are called as signals. Sometime in your undergraduate you might have learnt about interrupts. Okay. So you know interrupts are asynchronous events which occur and you need to handle them. So signals are just like that, just that they are software interrupts. So if I look at the definition of signals, they are asynchronous events that are notified to a process, and the process can respond through what is called as a signal handler. If that is not masked, it means the signal can be masked as well. So let us assume this is your process and you have written a signal handler here. This is a function and this is your main function that is running, and while it is you can put it in an infinite loop here. This is a signal that might be delivered to the process. So there are almost about 32 different signals. In fact, I have just listed a few of them, like sig interrupt, and every signal has a number. So sig int has number 2, sig term is 15, sig kill 9, sig segue 11, sig alarm 14, like this. So system assigned numbers are there. Now what these signals do? Signal interrupt, that is, if I press Ctrl C, this signal interrupt will be generated. Though this is an interrupt from the keyboard. So this process is running, if I say Ctrl C, sig int will be generated and it will be delivered to the process. Now how the process responds to this sig interrupt depends on whether there is a handler set up or not. Okay. If signal is not there, then the process will simply terminate. Okay. Otherwise, it will go to the signal handler and you may print that I am interrupted by signal interrupt. Okay. So you have the option to handle the signals appropriately. Now this is a hardware interrupt, that is, you cause the interrupt to occur. You can generate an interrupt from within the process, that is using a sig alarm. I think so, this one. So there is a function called as alarm, and you can specify delay of seconds. Let's say after 5 seconds I want sig alarm to be delivered to this process. And if you have set up a handler, again you can indicate who interrupted the process. Okay, so in this case it will be sig alarm and the number will be 14. Okay. Similarly, a child process can cause a signal to occur. For example, a child process stopped or terminated, then sig CHLD will be delivered to the parent process. Okay. So again, if you have a handler here, you know that the child has terminated and you have responded to the signal generated by the child. So signals can come from many different sources, and you can cause the signals to occur. Similarly, there is a signal called as sig-seg-v. This will happen whenever there is a segmentation fault. That is, you are trying to access a memory which is invalid. You just have a pointer int star p and it is not pointing anywhere, means it will contain some garbage value, and if you try to access that pointer content by using this, then there will be a segmentation fault. That is, you have crossed the boundaries of your memory and you have tried to access, and the signal generated will be sig-seg-v with number 11. So you should have set up a handler here to know what really happened when the invalid operation like this one was created. In fact, you should have made p to point to some other variable, let's say x, and you have declared x equal to 7 or something. Then there is no problem, it will go normally. But if it is not initialized like this and you are trying to access, p might be pointing to some invalid memory address, and that might cause a sig-seg-v signal. Alright, so there are 32 different signal sources, and which when they occur you should know how to handle them. Now, how do I handle a signal when it occurs? There are two ways of doing it. One is using a function called as signal, and second one is called as sig action. Now, this is the simplest way of handling a signal. However, it has many problems. One thing is, it is not POSIX standard. It means from operating system to operating system, you may not find support for signal and programs become less portable. Okay. Second thing is, when the signal has occurred and you are in the signal handler, if the signal again occurs, again the interrupt might happen, and repeatedly there will be a race condition. So you will keep looping in the signal handler only if the signal keeps happening continuously. So this is called as a race condition, which is not properly handled in signals, and that is why the use of signal is discouraged. You need to use API called as sig action. So how to use these two? First thing is, for understanding this is easier, we will go with this first, and then we shall see in great detail how sig action can be used to do the same thing but in a more robust way. That is, it will not allow race condition, and it is portable across all Unix operating system which are POSIX compliant. Okay. So is the concept of signal bit clear to you? Or you have any questions here?
It's clear, sir.
Okay. Yeah. Now let's see the program where I can create a signal handler and cause some signal to happen. So for that I have sig1.c. You require certain header files here, signal.h. You need to include. Now the way to set up a signal handler is void signal handler, and here it will receive the signal number, and you can check whether that particular signal is delivered to you. Signal handler received signal number equal to percentage d, we can put a slash n, signal number. Now it is as simple as this, just one function, just as we wrote thread handler. A signal handler has this signature, that is the return type is void, and it has only one argument, and that is the signal number. Now in the main, before you do anything, you have to indicate that this function is a handler for the signals that occur. So signal is the API. Now this signal handler is for which signal? First part is that you have to indicate the name of the signal. So you want to set up this for signal interrupt. That is Control C. When I press, the signal handler should be executed. So this signal handler is for handling interrupt signal. Now here you can be in a while loop, and possibly you can keep printing some message. After every second, so you can sleep for 1 second. So the main will keep looping, and while it is looping, if you say Control C, the handler function will be executed, and again it will be back. Let's see what happens now. Expected identifier, line number 4. Yeah, there is one extra bracket here. Dot C. As you can see, message from main is coming. Now if I say Control C, you see that signal handler received and signal number is 2. If whenever I do Control C, you will see that handler is executed automatically. Are you following this? How to write a signal handler?
Yes, sir.
Okay. Now this process, the main is continuing like this. We'll see how to kill that process. For that you execute in another terminal this. As you can see, the program which I wrote, which I was running, sig, is still running. I can send a kill signal for this. And kill signal, there is no handler. The default action is terminate that process. So 2720. Now you see here in your program, the process has terminated. It is killed by the kill command. Okay. Now there are certain signals which you cannot mask or ignore. They are going to be delivered to the process. So such signals are having very high priority. Like kill is a high priority command. It cannot be masked or ignored. Okay. So what is masking? We shall come to that a little later. But in principle, you understood how a signal can be generated and it can be delivered to the process, and the process can handle it appropriately. Similar to this interrupt signal, you can have an alarm signal. So let's look at that. Sig alarm 1.c. So here again I have a handler here. Same thing, just that I am changing the message hi, I am alarm signal and the number here. Now I need to first set up the handler for sig alarm. Now just note the spelling here. It is not sig alarm, ALARM, it is just ALRM, a short form. So the maximum number of characters allowed for mentioning the signal name is 7 characters, so that is why it is one less character. Sig ALRM, and then sig handling. Now, how do I cause this signal to occur? So you can call the system function like this. You can give the delay. After 3 seconds, sig alarm signal will be delivered to this process, and this process can either be in a loop or it can just pause. Pause. Now pause means it will be in a dormant state until the signal occurs. It will wait until signal occurs, and when the signal occurs it will go to the handler and you will see this message gets spread. Alarm 1.c minus O SA. Now until the signal occurs it will be just in the dormant state. As you can see, I am alarm signal number 14. So interrupt had number 2 and alarm signal as number 14, as I indicated in the table here. Sig alarm has number 14. Okay. So we can cause signals from different sources. Control C is one, call of alarm function is another. Okay. Now, as I told you, the use of signal has problems. That is, it allows the signal to be delivered even when it is in the handler. So repeated signals, if they occur, then there will be a race condition. So to avoid this, we have sig action. So let's see what is this sig action and how to use it. Now, as before, the signal handler will be same. Okay, but I am not using the signal function. You have to use a structure called as sig action. Now there are two things: sig action structure is also there, and sig action system call is also there. So there are two different things. The names are same, but this is a structure name and this is a system call name. Now what is this sig action structure? What all it contains? So let's look at sig action structure. It contains 4 members here. First is the signal handler that used to specify in signal function. So the first part of the sig action is the signal handler. As you can see, it is not returning anything and it is accepting an integer number. The second is if you want to display more about who caused the signal, like the PID of the process which caused the signal, or the details about when signal occurred and all that, you can have more details of the signal. So sig info is what is used to get the details of what really happened when the signal occurred. The third part is signal mask. That is, signals can be masked. That is, even when you press Ctrl C, you don't want signal to be delivered, you can mask it. Masking is a temporary thing. That is, you can unmask also, so that when you are in the signal handler, you don't want anybody to disturb you. You put a mask, and once you are done with the signal handling, you can unmask and then allow signals to occur. And there is last member, which is sig SA flags. You can specify additional things, and what is the purpose of this particular signal action. First thing is, if you want to display additional information about the signals that occur, then this SA flag should be SA sig info. And if whenever you are in the middle of a system call, for example you are reading from a file and signal occurs, then you go to the signal handler, and when the signal handler ends, you want to continue with the read operation. In that case, you have to say SA restart. as one of the flags. Then no child wait, that is you don't want the process to wait for the child process to terminate. So in that case, child no wait can be specified. Similarly, ignore child stop. If the child stops while the signal is being handled, you can ignore that. Like this, you have many flags here, and you can use only few of them or a combination of them using a or operator in between, like SA restart or signal info or signal no child wait. All three can be specified as SA flags. Okay, so we have sig action structure, and in that you have to specify all of these or few of these. Suppose you don't want additional, you don't want to display the information about the signal processes causing the signals. In that case, the second argument can be null. Okay, and mask also, if you don't want to specify, that can also be null. And you want default behavior like of the process, then you say SA flags equal to 0. That is, SA restart will be the default action. So let's see how all this can be done using the sig action. So first thing is you declare a variable of type sig action, struct sig action SA, and this structure is defined in signal.h. So signal.h must be included before you want to use sig action. Now as first member, SA handler will be your signal handler. Okay. And I am not using the additional information about the signals causing the processes causing the signal, but I want to specify the mask. So sig empty set, you don't want any signal to be masked, so you have to keep the mask empty by calling sig empty set, and you have to send the address of the SA mask. SA mask will get access to the mask variable, and its address should be passed as an argument to this, and the SA flags should be 0 for default behavior. And then you have to call sig action. The first argument is the name of the signal as before, and second argument is the address of the sig action variable, and third argument is null. Okay. Now as before, you be in a loop printing something, and whenever the signal occurs, it will call the signal handler indicating who caused the signal to occur, or the signal number delivered will be printed here. So it's exactly the same thing as before, little more complicated but more robust than the previous one. GCC sig action.c -o. So main is just printing this. If I cause interrupt signal by pressing Ctrl C, you will see that I am signal handler for signal number 2. Okay, so the main is just continuing with its action even when Ctrl C is pressed. Remember, signal handler is only a procedure that gets executed. It will not terminate the process. If you want to terminate this process, you have to go to another terminal, check the PID of the process, that is SA, which is having 2750, and you should kill it. Okay, so it gets terminated like that. Okay. Now signal action is a more robust way of handling signals, and as I told you, you can get the information about the process which is causing the signal. Now in that, I have another program to illustrate sig action more.c. In this, what I am doing is I am not only printing the signal number, I am also printing the process which caused the signal to occur. So sig PID is also displayed through the second argument info. Okay. The third argument is a context which is not useful as of now. So what you have to do is, as before, declare a sig action variable, set its members to different values, sig action equal to the handler, sig flags. As you can see, I have sig info and SA restart. So these two must be there whenever you want to use the second argument here. You want to display information about the process which caused the signal to occur. And then the mask is empty as before. You set up the signal handler, pass a second argument, and third argument is null. And be in a loop again. So you can have a print statement here. Is everything okay? I think so. You should have unistd. Now, if I want alarm signal to be delivered, you can just check that. Alarm after 4 seconds.
Sir, alarm spell mistake.
Okay. Yeah. We need to compile this. This is the sig action more minus sig action. So the main process is running. The alarm occurred now. Okay. After 4 seconds. Okay. But it did not display the process ID. What went wrong? I think so. We should have given little delay here. Because the handler did not execute. We will see what is the reason. Alarm clock is only displaying alarm clock. This message should get displayed, no? Okay, let me check with Control C. Yeah, with Control C it is working. Caught signal 2 from PID 0. Okay. So with interrupt signal, it displayed the interrupt signal number 2 and the PID of that process is 0. Okay, so whenever I say Control C, the operating system will deliver that interrupt signal to the process. Okay. If any other process is causing the signal to occur, then you will see the PID of that process getting displayed. I think so. Whenever you use alarm signal, possibly it is not capturing the PID of that process, the same process causing the alarm to itself. So that could be the possible reason. if I use only signal info and then not this restart. Then instead of a while loop, we can just pause here. Let's check with this. Oh, I did not compile this one. It is only saying alarm clock, but it is not displaying this caught message. This part it is not showing. But it is showing that it is coming from alarm signal. I need to check this, why this is not working. Now I am not able to display the signal ID and also signal number and also PID here. This is not getting executed. I will just check what is going wrong. I'll get back to you in the next session. But as you can see, using Signal Action API for handling signal is more exhaustive, and it provides you a lot of information as to what really is happening when the signals occur. Okay, and it will also provide you options to mask the signals. If you ever wanted to mask a signal, there is a function called as sigproc mask, using which you can mask a particular signal. Okay, so the syntax of that I need to check a little bit. So even if the signal occurs, you can mask that. So sa mask, and you say sig alarm. So what this will do is it will mask the signal from occurring. Okay, I think so. The mistake was that I have written sig int here. It should be sig alarm. Correct? Did you see the mistake here? I was setting up the handler for signal interrupt and expecting alarm signal to be handled. So this handler was working for signal interrupt, not for sig alarm. So the mistake was here. Let us see whether that comes through, and it displays the process ID as before, and we can keep this sigproc mask commented, and let's see whether that is happening now. // Okay, so now it is coming caught signal 14 from PID equal to 0. Again it is displaying PID 0. It should actually display the PID of the process which is causing the signal. Because the same process, this one is causing the signal to occur. So the info SI PID should print the PID of the process, but it is printing 0 here all the time. So we need to check whether this is right or there is some mistake here. Okay. So that part we shall see, and you can mask the signal using this sigproc mask. Okay. So I only need to check whether this syntax is correct. If it is correct, then it should work for us. No, I think so. It is. No, sig prop mask is incorrectly used. How? There is a different syntax for that. I think so. I have not worked on it, but we shall see in our next session how to use this signal masking to ignore the signals if whenever they occur. But most importantly, what you need to understand is how to use sig action to set up the signal handlers with so many options available to you. Okay, so this syntax you should get familiar with, and then we shall see how the signal masking can be done. All right. Okay.
So this third argument for sig action is always null.
Which one?
The third argument of the sig action.
This one?
Yes, yes.
Yeah, I mean, there are different options here. It's not always null. That you can make the signal persist or make it a safe signal action. There are different values to be put here. I think so. I have captured them somewhere here. Now the third argument has certain values to be specified. Using that, you can add additional features like make the signal persist. Okay, exactly what does this mean? I need to explore, and make the signal action safe. So, if whenever you have multi-threading, signal action should be safely executed. So, I think so. This third argument allows you to specify these additional features. Okay, so more on those details I will get back to you in the next session.
Sure, sir. Thank you, sir.
So I'll share the code with you. Please go through and try to execute. Could you experiment with some of these programs?
No, sir, I couldn't.
Not finding time?
I-
Some of you tried, Nikita?
yeah.
You tried, no? Okay. So only thing what remains is you have to go back and try these programs out so that you get familiar with the syntax of the programs. All right. So you shall see more on these things next time. Okay. Bye then.
Sure, sir. Thank you.